Yeah, hi everybody. Hope that you're all doing well, and we're going to move a little bit more forward into Chapter 9. We completed 9.1 where we looked at exponential functions, and the primary objective of that section was to be able to graph an exponential function and talk about the characteristics of them. Now we're moving into 9.2, and we're moving into two different types of additional functions. One of them is called composite functions, and the other one will be called inverse functions. Now, when we were in Chapter 2 in our program, that is the chapter where we really focused in on functions, and we operated with functions back in Chapter 2. We found out that two functions could be added, subtracted, multiplied, and divided. Now in 9.2, we're going to see another way of how two functions can be combined. And one of those that we'll start off with are known as composite functions. And we'll go to the board and we'll kind of give you a definition of what we mean by composite functions. Composite functions are two functions that get combined by having the output or the range of one of the functions become the input or the domain of the other function. Let me kind of rattle that off again. Composite functions are two functions, when combined, take the output or the range of one of the functions, and that output or range becomes the input or the domain of the other function. Now, to show an illustration of that definition as to how composite functions get combined, we're going to take a look at an imaginary kind of an example. I suppose it would be an example that could occur in a department store, or in the example that we're going to use a furniture store. We're going to look at two different examples of functions, and we're going to combine them based on the definition that we just articulated to you. Let's say that when we walked into a furniture store, there happened to be two different discounts that were being offered on the furniture in that store. One of the discounts, identified by function f, says the value of function f when the domain is x is equal to x minus 300. Meaning, in the furniture store, the discount that is being offered is they'll simply take $300 off of the original price. That's one of the discounts that was seen being advertised in the store. But as the customer moved around in the store, they noticed that there was another discount being offered for maybe a different area of the store. And that second discount was being described by a second function. G of x is equal to 85 hundredths, or 0.85, multiplied by the original price of the furniture. Now, what this function is really defining is, it's really defining that the store will offer a 15% discount on certain items in the store. If it's a 15% discount, you're saving 15 cents out of every dollar that furniture amount is, and if you are saving 15 cents out of every dollar, you're only going to be paying 85 cents of every dollar that the furniture is worth. So these were witnessed, let's say, by a customer to different discounts. And now, as I continue on with this illustration, it's going to become exaggerated. It's going to become a storyline that is likely not true at all, but to promote the idea of composite functions, just carry along with me with this fictitious story. Let's say the customer goes to the manager and says, you know, I want to deal with you, I want to buy some furniture, but I'm wondering if there is a way that that you can give me more of a discount than what I've seen advertised in the store. And to make a long story short, the manager, in a very agreeable mood, says, we're going to do this. We're going to let you purchase the furniture that you want to purchase, and we're going to do the following. We're going to give you both of these discounts, and we're going to give them both to you in the order that I am saying. We're going to take 85% of the price of the merchandise that you're going to buy. And then after we've given you 85% of that original price, then in addition to that, we're going to take $300 then off of that amount. Now, I said it was exaggerated, but this is how the composite function illustration will work. We're going to take 85% of the original price first, and then we're going to reduce that amount by $300. So the function that we're going to start off with to illustrate this scenario is the function f of x is equal to x minus 300. Now that's why I wrote that centerpiece right in the middle right here. We're not beginning with g. We're beginning with f. And here's how the composition of these two functions will work out. Item number one that I want to speak to and make sure that you understand is composite functions have a particular notation. A notation that when you look at it, it will always remind you that it's standing for composite functions. And here's the notation. F O G. It's a little o. It maybe kind of means f of g, but it's a little o that's in the middle. And what this f o g of x really means is this. It's equal to f of g of x. Now, I said in the definition, composite functions is a means of combining functions where the output or the range of one of the functions becomes the domain of the other one. So in the way that we've written this out, we're going to take the range value of g of x. We're going to take 0.85x, and it is going to become the domain of function f, which is equal to x minus 300. Now, I started off with the notation of these two functions being composite, written in this notation. But this notation is equivalent to f of g of x. Now, here is what we're going to do. We have identified function f right here, and after this equal sign, wherever we see X, we're going to put in place of X the expression that stands for g of x. And the expression that stands for g of x is 0.85x. So, in place of x, we're going to write 0.85x. That's going to give the initial discount. The manager is going to give the customer and make the customer pay 85% or 85 hundredths of the original price of all of the furniture that the person is going to buy. And then on top of that, take $300 off. What we just did here in this illustration, we took the output of function g, the range of function g, and we've made it become the domain of function f. That's really what we have done. So wherever we see x in function f, wherever we see x, we're putting the range value of function g, and that's the 0.85x, and then we're going to subtract 300. That is actually the transaction that is going to be done up at the cashier when the customer goes up and purchases the furniture. That is how composite functions work. Now, let's finish this one off by actually having the customer purchase merchandise. And let's say that the amount of money that the customer is going to buy in this furniture store has a value of $2,480. So here's what we're going to do. We're going to come down here and we're going to write the composition of f with g when now the domain is 2,480. And we're going to take that 2,480 and we're going to put it in place of x in this statement. And the end result will be the amount of money that the customer is going to have to pay, getting both discounts. Getting a 15% off, and then on top of that, a $300 reduction. And so we'll bring down the 0.85, and that's going to get multiplied by the overall original price of all of the furniture that the customer bought, $2,480. And then when that transaction is done, we'll subtract $300 off of that and we'll get the final price. Now, if we take 2,480, I'm going to try and scooch it right up here. I know I had the amounts somewhere else on a sheet of paper, but I don't have it right now, so we'll actually do the computation. And now we're going to multiply that by 85 hundredths. And we'll get a 0, and 40, and 24, and 12. We'll put a little placeholder, and we'll have a 0, and 64, and 32 and 6 is 38, and 16 and 3 is 19, and we'll add down, and I'll just kind of double check my work real quick right here. 24, 12, 8, 10, 11, and I think that is a 2 maybe. 8, 10, 10, 11, yeah, and move it over twice. $2,108. That's what the customer would be paying if he just got 15% off. But he didn't get just 15 off. because the manager is allowing an additional $300 to come off of that. And so the final outcome would be 2,108 subtracted by 300 bucks. We have 8, 0, and about $1,808 would be the out the door amount that the customer would have to pay, obviously not including tax. But that is the means of how composite functions get combined. Let me just say this without reading it up there. The output of one of the functions becomes the input of the other one. The g of x became the domain of function f. The other way, we could have worked it the other way as well, but we didn't in that particular case, but we could have. All right, I'm going to erase this little illustration right here, and we're going to do a couple of other examples of composite functions, ones that you'll primarily see in the exercises that we're going to be dealing with on them. So I just kind of want to get some things kind of cleared up a little bit. And then we'll go to kind of a separate little sheet that's going to show the information that we're going to transfer over this to this board. On this little 8.5 by 11 sheet of paper that Kristen will kind of zoom in on, we're just going to show you 3 additional examples of evaluating composite functions. Let's say we're given f of x is equal to 5x plus 6, and g of x is equal to x squared minus 11, and it says find each of the following. Let's say that we are asked to find the composition of f with g. I guess you can kind of look at it in terms of the word fog, but it's a little o, and it's the notation for composite functions, where f is going to be joined together with g when the domain is x. That's what they're going to ask us to find first. Then they're going to turn it around, and they're going to ask us to find the composition of g with f when the domain is x. And then finally on number 3, they will ask us to find the composition of g with f when the domain is -3. So I'm going to transfer those 2 functions up here. Let's say that we have f of x is equal to 5x plus 6, and g of x is equal to x squared minus 11. And on problem number 1, they're wanting this. They want us to find f composed with g when the domain is x. Now here's the instructions so that you know which one of those original functions we are going to be working off of. You'll always know which one you're going to be working off of when you look at the notation for composite functions, and whichever one of the function names appears first, to the left of the little o, that's the function that we're going to start off with. So, because it begins with f, we're going to start off by bringing down f of x is equal to 5x plus 6. And now I'll just bring down f composed with g when the domain is x. And now I'll even translate it to what it also means. This means f of g of x. That means the value of g of x is going to become the domain for function f. And so I'll just bring down an equal sign, and here's how it unfolds. You bring down that coefficient of 5, and you make a house after that. And in place of x, we're going to put the g of x expression. And the g of x expression is x squared minus 11. And then we'll bring down the rest of this function f. And now let's simplify it. And we'll have 5x squared negative 55 plus 6. And now we can write our summation statement. I can go to him, but I can also go to him. They are synonymous. The value of f when the domain is g of x is equal to 5x squared negative 49. We'll circle it, and there's the outcome. That I just did right there, that corresponds to that $1,880 that the client had to pay for that furniture. It's actually what was done. That's number one. Let's go to number two. Number two, they want us to find g of f of x. So we look at it. G is being composed with f, and g occurs first. So we're going to begin by bringing down function g. G of x is equal to x squared minus 11. And now we're going to find g of f when the domain is x, which is equal to g of f of x. So that means we're beginning with function g, and we're going to take the output or the range value of f, and that range value of f is going to become the domain of function g. So we hit our x variable right away, and in place of x, we're going to put the binomial of f5x plus 6. So we'll tuck that 5x plus 6, and according to this function, it's going to get squared, and then negative 11 comes after that. We bring down the equal sign. Now we could expand out the meaning of that, but I'm not going to do that because we should know pretty confidently how to square that binomial. So we're going to square it. Square the first term. That's 25x squared. Square the last term. And I'm not putting it here. I'm shoving it down a ways because there's a middle term that's going to have to go in there. Square the first. Square the last. And then the middle term is these words. Their product multiplied by 2 goes in the middle. Their product is 6 times 5x, 30x. Their product, 30x times 2, positive 60x, goes in the middle, and then minus 11. So we'll come down, and I'm going to write the value of function g when the domain is f of x is equal to 25x squared plus 60x plus 25. That's the value of g of f of x, or it's the value of the composition of g with f. That's him. And then finally, number 3. They want us to find the value of g of f when the domain is -3. Well, g comes first. We already did. We've already found the value of g when the domain is f of x. Now let's find the value of g of f of x when the domain is -3. So all we really have to do is substitute the value of -3 wherever we see x here. Because we just found the value of g o f when the domain was x. Now we're going to find g o f when the domain is -3. We'll just substitute -3 where we see x in this trinomial. So 25 times the quantity of -3 squared plus 60 times -3, positive 25. And now we'll just come down and follow the order of operations. 25 times 9 plus 60 times -3 plus 25. Well, let's see if we can do this. I believe 25 times 9 will be 225, -180, positive 25. Well, 225 added to 25 would be 250. I'll kind of put it right up there. And 250 coupled with a -180, I think that will give us 70. So the value of the composition of GOF when the domain is -3 will elicit a range value of 170. And I think we'll have that situation right there. Now that is a composition of functions. We've taken that amount of time for that. We'll just call the video at this particular case. And when we come back, we'll take a look at inverse functions. But just as a final summary statement, when we're talking about composite functions, we are combining the two functions by taking the output of one of the functions and having it become the input or the domain of the other one, and then operate with that and calculate out the result. That's composite functions. Now, in a concluding statement, the most important of the pair of functions that we're going to be talking about in 9.2 is the inverse functions, and that will come in the next video. Take care of yourself for right now, and we'll talk in a bit.